Hello everyone, this is the Earth Archives. I don't know if you like science fiction movies or literary works. Antimatter is a very popular subject in such works, but do you know what antimatter is? Who proposed antimatter? Have humans really discovered antimatter? Before the show starts, please help subscribe, like and turn on the little bell. This will help the Earth Archives grow. The show starts. Imagine a universe just like ours, but with one crucial difference: everything is reversed. The stars, planets, and even the atoms that make up life itself are composed of something that mirrors our own reality, a mysterious substance known as antimatter. This is no work of fiction. Rather, it is one of the most profound discoveries in modern physics. Antimatter, with its enigmatic properties and vast potential, stands at the frontier of scientific inquiry. But what exactly is antimatter, and why does it hold such fascination for scientists and storytellers alike? To understand antimatter is to embark on a journey through the very fabric of the universe, exploring both its theoretical foundations and practical implications. In this article, we will delve deep into the origins, properties, research, and cultural impact of antimatter, all while weaving together a narrative that is as captivating as the substance itself. The birth of an idea. The early 20th century, a revolution in physics. The early 20th century was a time of unparalleled scientific discovery. Albert Einstein had just introduced the world to his theory of relativity, fundamentally altering our understanding of space and time. Quantum mechanics was beginning to take shape, challenging the very nature of reality. Amidst this backdrop of scientific upheaval, a young British physicist named Paul Dirac was about to make a discovery that would change the course of physics forever. Paul Dirac, the theoretical pioneer. In 1928, Paul Dirac, a reserved and brilliant mathematician, was working on a way to marry quantum mechanics with Einstein's theory of relativity. His goal was to describe the behavior of electrons, which were already known to be fundamental particles of matter. The result was the Dirac equation, an elegant and complex mathematical formula that accurately predicted the behavior of electrons. However, the equation had a peculiar quirk. It implied the existence of particles that were the exact opposites of electrons. These hypothetical particles would have the same mass as electrons, but carry a positive charge instead of a negative one. Dirac's equation, in effect, suggested the existence of antimatter, a bold prediction, the positron. Dirac's theoretical particles, which he referred to as anti-electrons, were not immediately accepted by the scientific community. The idea that every particle of matter could have a corresponding antiparticle seemed too radical, too abstract. But Dirac was undeterred. He predicted that these antiparticles must exist somewhere in the universe, waiting to be discovered. He would later coin the term positron for the anti-electron, marking the first step in the journey toward understanding antimatter. From theory to reality, the discovery of the positron. The turning point came in 1932 when American physicist Carl Anderson was studying cosmic rays using a cloud chamber. Anderson was searching for new particles when he noticed something unusual. A particle that behaved like an electron, but bent in the opposite direction in a magnetic field. This particle, which carried a positive charge, was none other than the positron, the very antimatter particle Dirac had predicted. Anderson's discovery provided the first concrete evidence for the existence of antimatter and earned him the Nobel Prize in Physics in 1936. The implications of antimatter's existence. The discovery of the positron was not just a victory for Dirac's theory, it was a monumental breakthrough in our understanding of the universe. The existence of antimatter suggested that the universe could be far more complex than previously imagined. If particles and antiparticles could annihilate each other upon contact, releasing pure energy, what role did antimatter play in the cosmos? Could there be entire galaxies made of antimatter? These questions sparked a new wave of research and speculation that continues to this day. Annihilation, the dance of matter and antimatter. One of the most intriguing properties of antimatter is its interaction with matter. When a particle of matter meets its corresponding antiparticle, they annihilate each other in a burst of energy. This process, known as annihilation, releases a significant amount of energy, much more than any chemical reaction. The implications of this phenomenon are profound, both for understanding the fundamental forces of nature and for potential practical applications. However, the very fact that matter and antimatter annihilate each other raises a perplexing question. Why does the observable universe consist almost entirely of matter with so little antimatter in sight? The antimatter asymmetry puzzle. The Big Bang, matter versus antimatter. To understand the scarcity of antimatter in the universe, we must go back to the beginning, to the Big Bang. According to the prevailing cosmological model, the universe began as a hot, dense point that rapidly expanded, creating both matter and antimatter in nearly equal quantities. But as the universe cooled, matter and antimatter should have annihilated each other completely, leaving behind nothing but energy. Yet we find ourselves in a universe dominated by matter. This apparent imbalance between matter and antimatter is known as the antimatter asymmetry problem, one of the greatest mysteries in modern physics. Theories and hypotheses. Scientists have proposed several theories to explain the antimatter asymmetry. One possibility is that a slight difference in the behavior of particles and antiparticles, known as CP violation, led to a tiny excess of matter over antimatter in the early universe. This small imbalance could have resulted in the matter-dominated universe we see today. Experiments at particle accelerators, such as those conducted at CERN, have provided some evidence for CP violation, but the puzzle is far from solved. The quest to understand the origins of antimatter asymmetry continues to drive cutting-edge research in particle physics. Antimatter research in the modern era. Particle accelerators, the key to unlocking antimatter. The study of antimatter has advanced significantly since the discovery of the positron. Today, scientists use powerful particle accelerators to create and study antiparticles in controlled environments. Facilities like CERN's Large Hadron Collider (LHC) have been instrumental in producing antiprotons, antineutrons, and even antiatoms. These experiments have provided invaluable insights into the properties of antimatter and its interactions with matter. Antimatter in medicine, the power of positrons. One of the most practical applications of antimatter is in the field of medicine, specifically in positron emission tomography (PET) scans. PET scans use positrons to create detailed images of the body's internal structures, allowing doctors to diagnose conditions such as cancer with remarkable accuracy. The use of positrons in medical imaging is a testament to the real-world benefits of antimatter research, demonstrating how a concept once confined to theoretical physics can have a direct impact on human health. Antimatter as a potential energy source. The annihilation of matter and antimatter releases an immense amount of energy, leading some scientists to speculate about the possibility of using antimatter as a fuel source. In theory, antimatter-powered spacecraft could achieve speeds far greater than any current technology, making interstellar travel a possibility. However, the production and storage of antimatter in sufficient quantities pose significant technical challenges. Currently, producing even a tiny amount of antimatter requires enormous amounts of energy, and storing it safely is no easy feat. Despite these challenges, research into antimatter propulsion continues, with the hope that one day it could revolutionize space exploration. Antimatter in popular culture. Antimatter in literature, angels and demons. The concept of antimatter has not only captured the imagination of scientists, but has also found a prominent place in popular culture. One of the most famous literary depictions of antimatter is in Dan Brown's novel Angels and Demons. In the book, antimatter is portrayed as a highly dangerous substance that could be used as a weapon of mass destruction. While the novel takes creative liberties with the science of antimatter, it has undoubtedly contributed to popularizing the concept and sparking public interest in the subject. Antimatter in film and television, Star Trek and beyond. Antimatter has also been a staple of science fiction in film and television. The Star Trek franchise, for example, features starships powered by matter-antimatter reactions, a fictional technology that allows for faster-than-light travel. This portrayal of antimatter as a powerful and advanced energy source has influenced the way the public perceives the substance, blending scientific fact with creative speculation. Similarly, the movie adaptation of Angels and Demons uses antimatter as a central plot device, adding tension and drama to the story while highlighting the potential dangers of this mysterious substance. Antimatter in other media, comics, games, and art. Beyond literature and film, antimatter has appeared in various other forms of media, including comic books, video games, and visual art. In comic books, antimatter often serves as a source of superpowers or as a plot device for epic battles. Video games have also incorporated antimatter as a powerful weapon or energy source, adding a layer of scientific intrigue to their narratives. Visual artists have used the concept of antimatter to explore themes of duality, symmetry, and the nature of existence, creating works that challenge viewers to think about the universe in new and imaginative ways. The future of antimatter research. The quest for antimatter propulsion. Looking ahead, the potential applications of antimatter continue to drive scientific research. One of the most exciting prospects is the development of antimatter propulsion systems for space travel. Such systems could theoretically enable spacecraft to travel at a significant fraction of the speed of light, making missions to distant stars feasible. However, the challenges of producing and storing antimatter in the necessary quantities remain formidable. Advances in technology and a deeper understanding of antimatter could one day make this dream a reality, opening up new frontiers in space exploration. Antimatter and the search for new physics. Antimatter also plays a crucial role in the search for new physics beyond the standard model. Experiments at particle accelerators and other research facilities aim to uncover the fundamental differences between matter and antimatter, shedding light on the mysteries of the universe. These efforts could lead to the discovery of new particles, forces, or even dimensions, fundamentally altering our understanding of the cosmos. The study of antimatter, therefore, is not just about exploring an exotic substance, it is about probing the deepest questions of existence, ethical and philosophical considerations. As our understanding of antimatter grows, so too does the need to consider the ethical and philosophical implications of its use. The potential for antimatter to be used as a weapon, as depicted in popular culture, raises serious concerns about its future applications. Additionally, the exploration of antimatter touches on profound questions about the nature of reality, the origins of the universe, and the possibility of other forms of existence. Scientists, ethicists, and philosophers alike must grapple with these issues as we move forward in our quest to harness the power of antimatter. Conclusion: Antimatter and the human imagination. The story of antimatter is a testament to the power of human curiosity and imagination. From its theoretical origins in the mind of Paul Dirac to its discovery in cosmic rays and its depiction in popular culture, antimatter has captured our collective imagination in ways that few other scientific concepts have. It challenges our understanding of the universe, pushes the boundaries of technology, and invites us to contemplate the very nature of existence. As we continue to explore the mysteries of antimatter, we are reminded that science is not just a collection of facts and equations. It is a journey of discovery, driven by the human spirit's unyielding desire to understand the world around us.